All right, let's start with number one. It says, what is the correct IUPAC name for the compound shown below? And we're looking at this compound here. And what I always usually do is look for a group of substituents. But in this case, we have 1, 2, 3, 4, 5, all right next to each other. So pretty much you're going to start on one of these ends because there's only one that does not have a substituent. So I'm going to now say that we're going to go with alphabetical priority, fluorine over methyl. So I'm going to start numbering right here. 1, 2, 3, 4, 5, and 6. And then I can just say, okay, I know I have a cyclohexane, and I look at my answers, and cyclohexane is in all of them, so I know I got that right. And then I've got a 1 fluoro, 2 and 3, so dibromo, and 4 and 5 methyl. And if you wanted to just check this, I mean, you could say 1 plus 2 plus 3 is 6, plus 4 is 10, plus 5 is 15, and that would give you what your substituent count is. But like I said, if you went from the other direction and you named this one, 1, 2, 3, 4, 5, it would be 15 as well. So that's a tie, and so we break the tie by alphabetical priority. All right, so now I can go ahead and name this. I don't have any stereochemistry, so I don't have to say it's cis or trans, plus there's 5 substituents, and cis and trans really is comparing 2 substituents to each other. So stereochemistry is not something you need to know here. But now we can say remember, we're going to label these in alphabetical order. So fluoro's first, just kidding. Bromo's first, fluoro is second, and then methyl. So I would say that this is 2, 3, dibromo dash 1 fluoro dash 4, 5 dash methyl. Oh, dimethyl. That should be dimethyl. Dimethyl. Because there's 2 things. So let's make this dimethyl. Dimethyl cyclohexane. And then I'm going to go and look for my answers. So we said cyclohexanes in all of them. Let's see, 2, 3 dibromo. Well, there's only one that's got 2, 3 dibromo. But let's check my other ones. 1 fluoro and 4, 5 dimethyl. So it looks like B is the only option. C has 3, 4 dibromo. 2 has 1, 2 dibromo. So we have 1, 2, 3, 4, and 1, 2. If we had started our numbering from here, so if we had done it like this instead, 1, 2, 3, 4, 5, 6, we would have gotten a way higher substituent count. We would have gotten 1 plus 2 plus 3 plus 4 plus 6, and that's 3, 6, 10, that's 16. So that's not going to work. So just remember that if you're looking for a group, this is the wrong numbering. If you're looking for a group, you want to break the tie with alphabetical priority if there is a tie. 4, oh my goodness, 4, 5, 6. So if he wanted to change this question up, he could do something where he went, maybe there isn't a methyl group here. And so now how would you number this? Well, like I said, you look for that group of substituents, and here's the group. So this would still, now you would look, there's a tie still. There's 1 carbon in between this next substituent on both sides. So now you'd have to break the tie again with alphabetical priority. But in this case, you would start with bromine, and you would go this way. So your numbering would look like for this compound 1, 2, 3, 4, 5, 6. And then you just do the same process. Cyclohexane, it has a 1 and a 2 dibromo, it has a 3 fluoro, and a 5 methyl. So just be careful and look for groups. If there aren't groups, then look for alphabetical priority, or look for and then look for which direction is going to give you the next least substituent. So you want to travel the least to get to the next substituent. And like I said, here's a tie. So that's just another example of what it could be. Here's what it was. B is the answer. Okay. Which statement below best explains why cyclohexane adopts a chair conformation? Well, remember that we've got 3 different types of strain. We've got angle strain, we've got torsional strain, and we've got steric strain. Angle strain, our best example of angle strain is going to be cyclopropane, because it's got 60-degree angles in between all of these carbon-carbon bonds, and that's really strained. Torsional strain, this one will also have torsional strain. That is the eclipsing of atoms that are coming off of those carbons. And steric strain is what I like to look at when we're doing a chair conformation. It's the interactions between the axial atoms. This was a bad place to draw it. Maybe up here would be better. So if we're looking at a chair conformation, my chair is really bad, but that's okay. We've got an axial position here, here, and here, and they're going to have interactions between them. And you can take out your modeling kit and see this. The axial ones on the bottom will also have, where's my third? Here. Okay. They'll also have interactions. And then these two are kind of overlapping here. But they're the strain of those axial atoms. They're closer together than the equatorial ones. And that's what makes equatorial positions more stable, is that they lessen that steric strain. Steric strain. This is steric strain. I don't know if I've been saying that right, but this is steric strain. So our chair conformation doesn't have any angle strain because it's got an ideal angle of 109.5. It also doesn't have torsional strain because we've put all these atoms at equatorial positions. And so we're alternating which ones are interacting with each other, and they're not eclipsing anymore. This is really good to see on a model kit if you're struggling to understand what this looks like. Just make your model kit, put it in the chair conformation, and then look at how you don't see atoms really eclipsing each other when you turn it on its side. So for the chair conformation, our angle strain and our torsional strain are going to be decreased. So let's find one that has that in it. The conformation has decreased torsional strain and increased angle strain. That can't be right. This one says increased torsional strain, no. Increased torsional strain and increased angle strain, no. And then decreased and decreased. So the answer has to be D. Oops, I don't know why I did that. Okay, so D is the correct answer here. All right, which statement is true about the molecule after a ring flip? All right, now remember there's a few things that we remember when we're talking about a ring flip. We're talking about which way our substituents are facing. Are they axial or are they equatorial? That's what's going to change during a ring flip. So I look at the answers and I go, what are they going to ask me here? They're going to ask me about the 2 fluorine atoms being trans or cis to each other. Okay, well, trans and cis don't change in a ring flip. So we can figure it out from this diagram, and we don't even have to worry about it when we flip our ring. And then they're going to ask me about the bromine atom being axial or equatorial. Okay, well, I know when we flip the ring that whatever is axial becomes equatorial, and whatever is equatorial becomes axial. So now with that information, I can look at my ring without even having to redraw it and say, all right, they're asking me about the bromine atom. Let's look at that first because I know that's easy. It's axial. So if it's axial, it's going to become equatorial. So now I'm going to go into my answer key here, or my answers here, and it's axial right now, so it's going to be equatorial. So I'm going to cross out anything that says that the bromine atom will be axial. It's already axial. So that means C and A are out. Now I'm going to look at whether the the fluorine atom is trans or cis to each other. Okay, well, let's look at this. Let's number our ring just like we would. I'm going to number it starting at this bromine atom. 1, 2, 3, 4, 5, and 6. And then I can look at my bromine atoms, and I have a 1. Oh, I'm sorry, my fluorine atoms, I have a 5, and I have a 2. And you could really number this any way you wanted to. It doesn't have to be this way. If this is easier, you could number it like this. You could say this one is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. You could number it from this fluorine. It really doesn't matter. We're not going to move it anywhere else. So however you number it is up to you. And we're not comparing it to anything either. We're just looking at the relationship between the two fluorine atoms. So we've got this one and this one. They're both axial. And they're on a 1 and a 4 carbon. So we have a 1-4 interaction, and they're the same. And sometimes it's good to just write your notes. Like, I know that if I have a 1-3-5 interaction and it's cis, it's going to be the same. I know that if I have a 1-4 interaction and it's cis, it's going to be different. And then I can remember, well, if 1-3-5 is cis the same, then 1-3-5 trans must be different. And that means trans here must be the same. Because they can only be one or the other. If they're the same and they're 1-3-5, they can be cis. If they're trans and they're different and they're 1-3-5, then they must be trans. And the same is true for 1 and 4, or 1 and 2, or 1 and 6. Any odd and any even number combined together, you've got one axial, one equatorial, then you've got a cis relationship. If they're both axial, then you've got a trans relationship. If it's 1-4. So let me just write this out a little bit clearer. 1-3-5 same equals cis. 1-3-5 different equals trans. My cat is going crazy in the other room. 1-4 equals same. Well, let's do it this way. Different equals cis. 1-4 equals same trans. Maybe I should go check on her. All right, so, just try to make that connection. Back to the question we were asked. We have 1 and 4. They're the same. We can look at our notes and go 1-4 same. That's trans. So now we can eliminate. Are you okay? Now we can eliminate anything that says cis, and that means that B must be the right answer here. I know that was a lot of words to get to the answer, but I think if you just really focus on understanding this relationship, then you can look at this and see that if you have anything that's an odd number like this and an even number like this, and they're the same, that they will be trans. Okay, so this one's B. Okay, which of the structures below represents trans 1 isopropyl 4 methyl cyclohexane? All right, well, we just did this whole thing on cis and trans and 1 through 5 and 1, 4. So now we have a relationship here that we have a trans relationship. It's 1 and 4. And so we can go back, refer to our notes, and make this problem much easier. So we know we have a trans relationship. It's 1 and 4. That means trans 1, 4, they're going to be the same. So I'm going to number my carbons first, and I'm going to number these all the same way because this does matter. We are comparing something. So I'm going to start at my isopropyl because it is 1. So 1, and then I need to get around to 4. So I'm going to go this way, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Okay. Zoom in on them a little. All right, so I'm going to look at these first and say, all right, I've got these two. They have substituents on 5 and 1. 5 and 1. So they can't even be right. They don't even have the molecules numbered correctly. So those are out. Those just aren't even worth looking at any longer. I must have numbered something wrong because I should have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Huh. This one also is on the 5. I must have done something wrong. Oh, I didn't label this one correctly. Look, I started at this this carbon instead of where the isopropyl was. So be careful. You can number them wrong if you're not paying attention. This one should have started at 1 here, 2, 3, 4, 5, 6. Because I'm starting at isopropyl every time. My 1 carbon is always going to be where the isopropyl group is. Okay, now that I've fixed that mistake, I can look and see that these two, C and D, do have a isopropyl on 1 and a methyl on 4. Isopropyl on 1, methyl on 4. And I know that they're going to be, what did I say? The same because they're trans. So I'm going to look, this one's axial, this one's equatorial. That's not the same, so I can cross that one out. And this one is equatorial, and so is this one. So C looks good to me. I'm going to say the answer is C. And just to prove that you can number these in a different way and still, I'm going to number this where I go around the other way. 1, 2, 3, 4, 5, 6. I still don't have that 1 and 4 relationship. Now I have a 1 and 3 relationship. So as long as you follow the same, you start at the same place and you go around the same direction on all of these molecules, you'll end up with the same answer. Because I could do the same thing over here just for the point. I could say 1, 2, 3, 4, 5, 6. I still have a 1-4 relationship. I would number them all the same. I would start from the isopropyl and go around one way or the other. Go around this way on all of them. But that's just to say that if you went this way instead on all of them, that you would still get the same answer. It's not so much that you have to follow a direction when you number, as long as you start at the same, where that substituent is. And because they told us it's 1, that's why I decided to start with isopropyl at 1 every time. All right, which of the chair conformations matches the structure shown below? All right, so we're looking at this, and now we're comparing chairs. So again, let's number our carbon ring. And here I am going to look for those groupings. I am going to number it sort of like it's important. I don't know. So I'm looking for groups. Here's a group of 2 methyls. And then I'm going to say, okay, if I go this way, it's a shorter way around. There's only 1 carbon in between these substituents versus 2 carbons in between this way. So I'm going to say, here's a group, and I want to number and go this way. So this will be 1, this will be 2, 3, 4, 5, and 6. Now I'm going to number all of these molecules the same way. I'm going to start at the substituent here and go 1, 2, 3, 4, 5, 6. I'm going to start here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Okay. And so now I can compare apples to apples. I have the relationship between these two is cis, and they're 1 and 2. So they're an odd and an even number. I can come back up to my note and say this is cis, 1, 4, different. Okay, so now I know that they are going to be different. That means 1 will be axial and 1 will be equatorial. It doesn't necessarily matter which is which. And then I want to just go back really quick and look at my molecules again, because remember in this last one, they had 2 that were numbered wrong. So let me make sure there aren't any numbered wrong. So I have a 1, I have a 4, I have a 2. That's good. I have a 1, 2, and 4 here. I have a 1, 2, and 5 on this one. So that ain't good. I have a 1, 2, and I have a 5 on this one. So that ain't gonna work either. So those 2 I'm just gonna immediately cross out. Okay, so back to my A and B. Those are the only 2 answers that could be right because they're numbered correctly. I mean, they're set up correctly. They're on the right carbons. All right, so I need 1 equatorial and 1 axial. So let's say I want my 1 to be either or. I just want them to be different. And so A looks like they're different. This one's axial and this one's equatorial, whereas these are both equatorial. So B is already looking kind of weird to me. I don't like it. But let's just double check. It's always good to triple check. Let's compare now 1 and 4. We have another 1-4 interaction, but now we have something that's trans because of the dashes and the wedges. So let's go back up here. We have a trans. They must be the same. So is 1 and 4 the same? Yes, they're both equatorial because this one's also equatorial, and that's what we want this one to be. And so that's good. That looks like the best answer to me. And I mean, there's other ways you can kind of go about this. I think if I tried to explain them, they might be confusing, so I'm not going to explain them. But I think this is the easiest way. I think making a note on your test or on your quiz, just to remind yourself of the relationship, then you'll be able to get these pretty easily. So A is correct here. Okay. Which of the compounds below would have the highest combustion per mole of substance? This one, highest heat of combustion per mole, that means it's got the highest energy. It's B. I know that because this has so much strain. It's so strained. This one's going to have less. So they should go. This one's got greater than this one's got greater than this one's got greater than the cyclohexane over here. And that's just something, I guess, to remember. I don't know how else to explain it. Dr. Hill may have explained it better in his video, but this has a lot of energy and it's very strained, so it's going to have a lot of heat combustion. It's going to release a lot of energy when it's broken. Okay. How are the 2 compounds below related? All right, well, Let's number our chain because that way we can look at it and compare it properly. So I'm going to start from this side because the bromine would typically get the higher priority than a methyl. And since there's a tie on the numbering, I'm just going to start from here. So 1, 2, 3, 4, 5, 6. However, for this purpose, again, it doesn't matter as long as you number them the same. So don't get confused and number this one like this because that's not right. We are looking to be closer to the bromine. That's where we're going to start. We're going to start here and we're going to go this way because we want bromine to be on the same number carbon, right? Because they're all either isomers or identical. And so we're not like, it's not like a different compound. I mean, it's not a completely different compound. So we want to number them the same. All right, so now that I've numbered it, I can look and say, okay, we have the same molecule, so that's good. I mean, we have 2 chiral centers, and the chiral centers both have the same substituents. And it looks like we have 2 chiral centers. So it's not a mirror image. So it's not an enantiomer. It's not a constitutional isomer. They're not identical because one's now trans. And if we change some, but not all, that is a diastereomer. So I say it's D. It's because we changed some, but not all. I checked to make sure that they were in the same place, like on the same carbon, the substituents were, and they were. So I'm going to go with diastereomer because we've only changed this bromine from this bromine. The methyl stayed the same, and they're on the same carbons, so nothing else has changed. If you were looking at the enantiomer, just to show you what that looks like, we would have, let's just draw this out again. We'd have a methyl here and a bromine here. So to draw the enantiomer, I would look at the chain. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Or 2, 3, 4, 5, 6. Yeah. 2, 3, 4, 5, 6. It's kind of funky. 2, 3, 4, 5, 6. Okay. And then I'm going to draw its mirror image, right? So I've got 1 carbon on the 3rd carbon. I've got a bromine that's like here, and I've got a methyl right here. So now I've drawn the mirror image. They will have different chiral centers. They will have different absolute configurations. Absolute configurations is just R and S. So these 2 molecules will have the chiral centers both will be a different configuration. What I mean is, if you look at bromine's chiral center here, you've got 1 carbons, HH. This one's 2. This one's 3. 1, 2, 3. That is hydrogens in the back. That is R. This one we've got 3. This one is going to be 2. No, this one's going to be carbon, carbon. This one's 1. HH. CC, yeah. This one is 2. So 1, 2, 3. This one is also R. Hydrogens in the back. On this side, we've got, let's see, bromine is 1. Then we have, we have 2 here and 3 here, I think. 1, 2, 3. This is S. On the other chiral center, we have 3. This one is 1. This is 2. 1, 2, 3. This is also S. Okay, so what I'm trying to show you here is that enantiomers, they have different absolute configurations. That's each chiral center. So if you just look at one chiral center, this one, and this one, now they've changed R versus S. That's how you can tell it an enantiomer, because they'll switch absolute configurations. And that's what he was saying about, like, it's hard to isolate enantiomers out because they're very similar in all of their properties. They just spin light in different directions. This is telling you something about the light rotation. All right, so that is that. It's diastereomers, but this is an enantiomer, just for funsies. Okay. What are the configurations of chirality centers in the corresponding molecule shown, or the compound shown below? All right, so let's see, how many chiral centers do we have? Well, it looks like we have 2. They keep saying something about 2. So let's see, this looks like 1 here, and 1, 2, 3, 4. This looks like 1 here. Remember, I can ignore all of those methyl groups. I can ignore double bonds. So now I'm going to take this one at a time. I have a chiral center here. Chlorine gets 1. Methyl is going to get that 4 spot. And now it's between these. So I've got, if I'm looking at one carbon at a time, I've got this carbon here and this carbon here. And that's CHH because it's bonded to this carbon. That's where that C comes from. And this one's bonded to this carbon, so this has a CHH as well. So they tie. All right, let's move to the next carbon. Let's move to now this carbon here and this carbon here. This one's got H, 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 and this one is C, H, H. So this one wins. So now we can say that this is 2. So let's go back. I'll erase all my scribble scratch here. This is 2. That must mean this is 3. So now I've got 1, 2, 3. H is in the front, or my 4 groups in the front. This looks like S. It must be R. Okay. Let's move on to this next chiral center. Okay. I have hydrogen in the back now, which would be over here. But I don't even really need to worry about it because it's in the back. We know it's number 4. We're not even going to look at it. So I've got a carbon, I've got a carbon, and I've got a carbon. So they all tie, so we need to look at what they're attached to. This carbon here is attached to 1, 2, and a hydrogen. So this has carbon, carbon, hydrogen. And we're looking at this one. Then we can say this carbon is connected to a carbon, and there's an invisible hydrogen. So this is CCH, okay? And then we've got our last one here, which is got a C here, and then 2 H's, so this is CHH. All right, so this one loses. This carbon here, it loses, so this is going to be our 3. And I'll make it blue, 3. And we have a tie between these 2. So now we need to move out to the next carbon. So now we're going to look at this carbon here and one of these carbons. It doesn't matter which one you choose, so let's choose this one. Okay, so I'll erase these so we can get a clear view. And this, I have this carbon is bonded to a hydrogen, and that's it on this side. So we need to go back and look at this and this. That counts as 2 C's. It's the same on both ways. So we're looking at this carbon, we can say CCH because we're counting that double bond and the H that's attached out here. And then this carbon, we've got HHH. It's a methyl. So this one wins. So this is going to be our 1. Number 1. This will be number 2. And now we can go 1, 2, 3. This looks S, and it is S because hydrogen's in the back. I'll erase all my scribble, and we can mark this S. So now we can say, well, both aren't R and both aren't S, but one is R and one is S, so that's good. C is the answer here. Which of the following is a Newman projection of the compound shown below? Okay, So my way of doing Newman projections and figuring out compounds, first of all, I would probably notice that this is chiral, which means it has R and S configurations. So I'm going to use that to my benefit. But I'm also going to look at my molecules as a plane of symmetry, or not a plane of symmetry, but just a plane, because I like to draw mine as sawhorses, however you call it. And I like to make these on this side dashed and this side wedged. That's just my way. And then the ones in the middle are in the field, in the plane. So now I can draw this and say my front carbon, which I'll make pink right here, it is going to be methyl, bromine, hydrogen. And the one that we don't see is the carbon-carbon bond that goes from this front carbon to this back carbon. And so it's going to the back. Well, it's in the plane, but I visualize it this way. And I'm going to call it R. When I draw that back carbon, I can say we'll draw it in blue. Okay. We can say, okay, we've got bromine coming up, bromine. We've got hydrogen coming up, hydrogen. We've got methyl coming down, and we've got this R group connecting to the other R group. This R group is kind of like the same thing because they're really just each other, right? So now I can number these and determine what their configurations are. So I didn't mark this hydrogen. This is a hydrogen. So whenever we have hydrogen, methyl is going to be our third one. So I can say that this is 3 with confidence. This is 1. This has to be 2. This is 1. This is 4. This is also 4. This is 3. That means this is 2. Cool. Now we can go 1, 2, 3. This looks S, but hydrogen's in the front, so this one must be R. And this one, 1, 2, 3. This looks S, but this one's in the front. It must be R. So 1, 2, 3. Yes. Okay. So these are both S. So we have S, S. Let's look at our molecule that we have here just to compare to really quickly. 1, we can say that this one is carbon connected to a bromine versus this carbon connected to 3 H's, H, H, H. This one's Br, C, H. Those are the 3 things connected to it. So it's got another carbon over here. Okay, so this one wins. This is number 2. So our hydrogen's in the back over here, and it's always 4, and then this is 3. So we have 1, 2, 3. Hydrogen is in the back, so this is R. That's the first one. Let's look at the second one. We've got 1. The groups are going to be pretty much the same. This is going to be 3. Our hydrogen's in the back. It's number 4, and this is 2. 1, 2, 3. This is also R. Hydrogen's in the back, so we don't have to think about it. This one is also R. So that is I wrote S here when I meant R. R, R. I hope you catch my mistakes when I make them. So this one's R, R, and so is the one we're comparing it to. So that looks like a pretty good candidate. I'm going to just circle that. I like that one. And you can do this with all of them. You would just go through and say, like I like to do that line, and then say everything on the left is in the back and everything on the right is in the front. And then just draw them out, you know? So let's go ahead, just do this, and then hydrogen out here for my front carbon. Remember, we're going to do the front one first, always. So that's this one. H. Br is on a wedge, and then our R group comes out. And then the back carbon has a bromine coming up. It's got a hydrogen coming out. and it's got a methyl sticking down, and that R group connects in the middle. Make it a little bit more. There we go. And so this is the back one. This is the blue one. You get it. Okay. And then they all have the same rankings, so you can just go ahead and number them really quickly. 1, 2, 3. 1, 2, 3. Hydrogen's in the back this time. This is S. It looks S. It is S. So this one's S. Or S down here. This one, 1, 2, 3, 4. 1, 2, 3. This one is also S. Okay. Let's see what else we got. We've got hydrogen and bromine here. So we've got these in the back, this in the back, this in the front, this in the front. But on our front carbon, we've got 2 bromines, so that don't work. And we've got 2 hydrogens. This isn't chiral at all because we have 2 of the same groups on the same carbon. Remember, if we've got more than one of the same group, it can't be chiral because then you can just rotate it all kinds of ways and you'll never get chirality. So this one's out for sure. This one's like not chiral. No chiral centers, really. Better way to say it. No chiral centers. Okay. And then this last one, these are on dashes. These are on wedges. And we can draw this one really quickly. Let's make the front one pink. So this, we've got dash, 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 H. We've got methyl. We've got bromine on a wedge. We've got our R group coming back. We've got, our back carbon. This one here, here, and here. We've got a hydrogen coming up. We've got a bromine coming up. We've got a methyl coming down. We've got our R group coming out. Again, number these quickly. You've already got the answers. We know this is 1, 2, 3. We've already done this. 1, 3, 2. Okay, so 1, 2, 3 on this one. This looks S. It is S because H is in the back, so this is S. And this one is 1, 2, 3. Again, this one looks S and H is in the back, so this should also be S. I'm not on this question. I'm on this one, so this one is S, S. So A is the answer, and you checked that by your chiral centers. And you didn't have to do all that brain twisting trying to figure out how the molecule lays flat and all that junk. All right. Which of the following compounds is miso? Well, lucky us, we literally just did this in the last problem. Is this actually S? Yes. Okay, sorry, I'm just checking my work here. And this one is S, and this one is S. Okay. Something seems wrong about these. I think I've done something a little bit incorrect, so let me just check my answers here. This one's going S. This one is going S. This is 4. 1, 2, 3. 2, 3. That's S. This is S. This one is S. This one is S. Did I draw this correctly? Oh, hydrogen's in the front here. I knew something was wrong. Sorry about that. Okay, hydrogen's in the front here. So this is actually 1, 2, 3. It looks S. Looks S. It is R. This is R, not S. I thought that was weird. Okay. Again, I hope you catch my mistakes. I hope you go, that's not right, Rachel. That's wrong. All right, so good for us. We just did all of those. We know this isn't even chiral, so they're asking us to find the miso compound. And since we've just determined the chirality, and the absolute configurations for all of these compounds, now we can pretty easily figure out which one's meso. And it's the one I messed up. That's why I knew I messed it up. Because remember, if we have symmetry, we can cut this in half and say there's an H and a BR on both sides, right? And we can cut it in half and we can say they have two different chiral centers, then this is meso, because those two absolute configurations cancel each other out. And we just did all that work up here to figure out their chiral centers configurations. And so this one is the meso compound right here. This is B. That one was A. Remember that those chiral centers cancel out. You have to have symmetry for meso. Meso, you want symmetry. And so you want different absolute configs, aka RS or SR. You want it to be like that. Alrighty, how many optically active compounds are there? Well, here's another meso question. And so we want to be able to cut these in half, basically, and have some symmetry. So here, you can cut this atom in half. You can also cut this one in half. And now we have symmetrical things. You have a dashed one here, and no matter where you cut it, if you cut it in half here, it's not symmetrical because they need to both be cis or trans. They can't be, this one can't be trans and this one's cis. That would make it symmetrical. So there's only one actively active compound. These two are not, because they've got that line of symmetry. These are meso. Yeah. All right, identify the true statement below. Alrighty. So I look at the answer key first and say, I'm comparing 1 and 2. I'm also comparing 1 and 3. And none of them do they say I'm ever going to compare 1 or 2 and 3. So I'm only going to be looking at those. So let's start with 1 and 3. Let's start with 1 and 2. I'm looking. Is there anything different about these? Well, there's something weird going on here. What is it, though? They've literally just switched. They've just switched these. They didn't even change their cis-trans. I mean, they're trans to each other, but chlorine is still on a wedge. Chlorine is still on a wedge here. So that's the same. And that means methyl here is still in a dash. So nothing has changed between these two. They're identical. So we can cross out diastereomers. Now we're just looking at 2 and 3. Well, these are still the same. And only one thing has changed, this methyl group. So I'd call that a diastereomer. Because some, but not all, changed. Smokey, leave it alone. Leave it. Leave it. Okay. So some but not all changed. Those are diastereomers, and they're definitely not enantiomers, because not only one changed. All right, so that's going to be D. All right, how many chirality centers are in a compound shown below and what are their configurations? All right, we can cross out all these methyl groups. No. This also is not one. It's got 3 of the same group attached. Be careful, this silicone is one because it's got 1, 2, 3, 4 groups attached. 1, 2, 3, 4. This oxygen isn't one. It's only got 2 groups attached, and it's got 2 lone pairs. That's not a chiral center. But this one is 1, 2, 3, 4. That's good. Remember, we can ignore H. We can ignore any CH2s, and we can also ignore double bonds. So let's figure out what their chiral absolute configurations are. All right, looking at this silicone, we've got a C, and a C. So that didn't help us. but this C is attached to three C's, C, C, C. This one is attached to an oxygen and two hydrogens, O, OH, H. And this one's attached to three H's. So this one gets that third, because there's a hydrogen that gets the four. This OHH, it wins, it's one, and that means this one is two. And then we can take 1, 2, 3. That looks like it is S, but because hydrogen's in the front, it's R. And I can clean up some of this so we don't have to look at all my scribble. So this one would be R. This one, we've got chlorine, it gets number 1. We've got a methyl, it gets number 4. We've got an oxygen and we've got a carbon. Oh, oxygen's going to get 2 and this is going to get 3. 1, 2, 3. This looks, what is that? S. Hydrogen's in the back. It is S. So I'd say this is S. Get rid of my scribble. So, yep, there's 2 chirality centers. This one's out. And the one is, and one is S and one is R. So that one is C. All right. Identify the true statement below. A pair of enantiomers will have the same boiling point, and each molecule will rotate plane polarized light to equally in opposite directions. That's correct. Remember that enantiomers, I said this earlier, they have very similar properties. They're going to have the same boiling point. They're going to have the same melting point. They're going to have the same molar mass. They're going to have the same density. All of their physical properties, for the most part, will be the same. The only thing that's different is their RS configurations and their positive, negative configurations, which we talked about briefly in the beginning of the chapter on chirality. That was like levitro and dextro, whatever. That's how light is rotated. They literally rotate in the exact opposite direction. That's why when you have that racemic mixture, and it's 50-50, it gives you no rotation because they're canceling each other out. They're going in the exact opposite direction and canceling each other out. So that's what that is. So this one's the right answer. And just convince yourself of that. I mean, plane polarized light is in equally the opposite directions. That's correct. But different boiling points is not. Different boiling points is not correct. Same boiling points is, but they don't rotate light in equally the same direction. So that's out. These are all out. The correct answer is A. All right, what type of reaction is shown below? Well, we have iodine attached here, and then we have OH attached here. So something has swapped places. These have literally swapped places on both sides. They're in opposite places. So this has to be a substitution reaction. Yeah, it's substitution. And that's just because this and this are literally in different places. Yeah. I hope that one's pretty straightforward. Which statement is true about the reaction below? Is that the same reaction? It sure is. Okay. What is true? Well, let's look at it. Remember, this is where I like to start writing down electrophiles and nucleophiles, electrophile and nucleophile. And I like to be like, my electrophile is going to be partial positive and my electrophile is going to be partial negative. I like to kind of underline them and color code everything because I learn by colors. I don't know. Colors help me learn. Okay. So I see I have this negative here. That's definitely that. So this has to be my nucleophile, right? Because it's negative and it wants to get some positive in it. And that means this is my electrophile. All right, so hydroxide is what we're looking at here. That's what they're asking us about. And we're saying it's a nucleophile. So we're going to cross out everything that says it's electrophile because that ain't right. And we said that iodoethane, however you say it, it's our electrophile. So I'm going to cross out anything that says it's a nucleophile. So now I have crossed out A, I have crossed out B, I have crossed out C, and that leaves me with D. I'm going to double check. Hydroxide is a nucleophile. Hydroxide nucleophile. And iodine is an electrophile. That's good with me. That's D. Remember, this is like that 1 through 5 stuff. You write it down and you can always refer back to it. And that way you know it, you write it down, you don't have to go, what was it again? Oh man, now that I've like looked at all these problems, I can't remember. It's right there in your paper. All right. What type of reaction is shown below? All right, well, we've gained products here. And we've lost something on this organic molecule. Right here, the iodine has gone away. And yeah, so this looks like it's an elimination. We've gained product and we've also eliminated iodine from our organic compounds. I'm going to say B. B is the correct answer here. Which atom is most polarizable? This is just knowing that as the further down you get on the periodic table, the more polarizable they become. And I think Dr. Hill does a good job of explaining this, so you may want to watch his video for number 18. He seemed to have done, I didn't watch it, but he seemed to have done a good job of explaining that. The answer is D. Iodine's lower down on the periodic table. This is actually in order. They're in order here. Iodine's the answer. Which atom of the molecule is likely to act as an electrophilic site? Okay, this is where I come in with my red and blue and I start marking things. I'm like, okay, this is negative. This is negative. That means these two things are pulling away from B. B is positive. All right, A is like a methyl group. I don't even know how to mark that really. So I'm not going to because I don't need to. Because I see B is positive. And remember, you go back up to my little note here. Electrophilic blue. What are we looking for? Electrophilic site. Perfect. I know that's B. And remember, we figured this out because we're looking at that electronegativity. And we're seeing that these real electronegative elements are pulling electrons down, leaving carbon in the middle here with not as many electrons and leaving it with a partial positive charge. All right, what is the organic product? What organic product is obtained from the mechanism shown below? All right, well, this one is just simply following arrows. So we can see that the bromine is going to take both of those electrons from this bond with it. So it's going to end up being alone. It's like not even going to be, it's going to like build a wall over. It's like, I mean, it may eventually get back in there, but just what our arrows are showing us right now, bromine ain't in it. He's like going to get in his rocket and he's going to jet off. So bromine's out of there. Now our nucleophile, this oxygen or this carboxylic, this ketone looking thing, it is attacking an HC, a CH3. You know what I'm trying to say. And so it's going to, now this CH3 doesn't have those electrons that bromine took off with. So now it's going to connect to that OH. So the only one without bromine in it is D. That's the answer. And it does have that kick. Remember, this is what we started with. O right here. And we added the CH3 group. And this one doesn't have a CH3 group. It just has bromine. So it can't be it. This one does have that CH3 group. So does this one, but it's really a CH2 group. So that means hydrogen would have had to get pulled off by something. I don't know. These are just wrong. Bromine shouldn't be here. The arrow didn't say bromine stuck around for something. So remember, bromine's a leaving group here. He's jetting off. The answer is D. Which of the following compounds cannot act as a nucleophile? This one is just knowing that what is it? Boron's unhappy. Boron only has 3 valence electrons, which means it can bond to 3 things. But it's got this this empty orbital, and it wants electrons. So it's always going to want electrons. It'll always be an electrophile. It'll never, ever act as a nucleophile. The rest of these have a bunch of lone pairs. Nitrogen has lone pairs. Phosphorus has lone pairs. Oxygen has 2 lone pairs. So they're all going to be nucleophiles. They're all going to try to get that positive charge. So that's just knowing that boron's always unhappy. All right, what is the major product obtained from the addition reaction of HBr with ethylene? All right, we've got it down here. Ethylene, ethyl, methyl, that's, I always go through my head, methyl, ethyl. Ethyl is 2. Ethylene is a double bond, and we're adding HBr to it. Bromine's going to take those electrons. The double bond is going to attack the hydrogen there. We're going to end up with bromine, negative. And we're also going to have a pick your spot. Remember that this double bond gives a positive to one side, and it lets the hydrogen go to the other side. So that's the spot I picked. Now my bromine is going to attack this. But see, that this step wasn't explicitly shown up here. That's why that's why bromine jet rocket. I don't know where it went, but here it is. Because the other step wasn't explicitly shown, we didn't add bromine back to this equation. But here, he's asking for the major product. So now we're going to add bromine back, and we're going to get this ethyl is still there, and now we're going to kick it with the bromine attached. So A is the answer here. We got rid of that double bond. We can't have a triple bond. That doesn't make any sense. This doesn't either. This really makes no sense. This is like, why would it do that? So A is the answer here. You know, it's always a good idea to look at the answers and be like, does this even make sense? What is that? Like, does this make sense? What is that? Why would there be 3 bonds? That doesn't make any sense. And 2 bonds, well, we got rid of one of those bonds. That doesn't make sense. And this is just like, why? That would never happen. Okay. Which statement must be true about the reaction with a KEQ equaling greater than or less than 1? Remember my little trick for KEQ is that if the arrow points towards the KEQ, I call the KEQ my system. This is my system. Then heat is going into the system. That means that this reaction is endothermic or endogonic, however you want to say it. I'm just going to say endo because it's the same prefix. And when something is endo, that means that delta H is positive. And remember we said that you can say delta G is sort of equal to delta H. That means delta G would have to be greater than 0, right? Because it's positive. That's what positive means, greater than 0. We just said that this reaction's endothermic or endogonic, so that ain't right. The reaction favors products. The arrow thing is another way to it's really easy to so let's erase this. KEQ, greater than 1. That means the reaction goes towards the reactants. So there's a few ways to look at that arrow. You can say it's endothermic. It's also favoring reactants. And it's pointing towards the reactants, right? I mean, it's pointing in the direction of where the reactants would be. So it doesn't favor products. That's wrong. And we don't really have enough information to say anything about delta S. We know that it's greater than 0. So B is the answer here. B. Okay. Which of the following is the strongest electrophile? Well, remember, let's go back to my notes. Electrophiles want positive charge. So the first thing I'm going to look for is a positive charge. Oh my gosh, here's a positive charge. It's got to be A. That was easy, right? I'm telling you, make a note and refer to it. It'll help you out every time. These are like this. These are just like, this is negative. Like, absolutely not. It doesn't want more negative. H2O has these 2 electrons. Probably not. This also, probably not. This has a positive charge. This is totally the answer. All right. Which statement is true about the reaction below? We saw this reaction already. We know it's a substitution. Let's look at what it's doing. Remember we said that let's just say it wants to know if hydroxide is acting as an acid or a base. Okay, let's look at what hydroxide is doing. There are 2 definitions for acids and bases. There's the Bronsted-Lowry definition and there's the Lewis definition. I'm going to use the Bronsted-Lowry here because it makes more sense in this situation. We have OH. It's reacting with something. On the product side, we get H2O. I'm looking at what OH is on the reactant side and what it's become on the product side. It looks like it's gained a proton. Okay, if it's gained a proton, it means it's a base. So the Bronsted-Lowry definition is proton donor is an acid, and proton acceptor is a base. And I remember this because all acids have like H in front of them, HCl, HBr, all the strong acids, HI, so on and so forth. So an acid is giving up that front proton, and a base is going to accept it. So our base accepted a proton. This has got to be our base. So I can get rid of anything that says that hydroxide's acting as an acid. That ain't happening. Now, the entropy increasing or decreasing thing, that threw me off somewhat, but what we're looking at here is that we've got actually more products than we did reactants. So entropy will increase in that case. So the answer is B. I didn't get that right because I picked it was decreasing. I didn't know what the heck was going on with entropy. But that's what's happening. The more products you have, the more entropy you will have, the more kind of chaos there is. And then here, how many transition states and intermediates are present? All right, well, we know that our transition states are our peaks, and our intermediates are going to be the troughs in between 2 peaks. So we've got 2 transition states, and we've got 1 intermediate. This is just understanding how these graphs work. You've got one thing happening. This is a hump to get over something. So once you're over it, you're forming something, and that's your intermediate. This is where the reaction starts to change from reactants to products. And then we have 2 things happening. Then our intermediates climb up another hill, they transition here, and then they form products. So we have 2 transition states, so these 2 are wrong. And we have 1 intermediate. So it looks like C is the correct answer here. All right, I'll come back and make a video on this B part, so I have a little bit more room.